All right. So now I'm going to give you the general formula for a Taylor polynomial of degree n near x equals 0. Okay, so this is near x equals 0. So the general formula is that it's f of 0. So let me start way over here. So f of 0, right, because we want the value of the function to match at 0, plus f prime of 0 times x plus the second derivative at 0 over 2 factorial, which is just 2, but we'll see the pattern here. X squared plus the third derivative at 0 over 3 factorial. So you might have noticed, whoops, what's happening there? It's very strange. All right. You might have noticed the coefficients coming down as you take more and more derivatives. And so we end up with these factorial terms in there. And then so on, right? There's a pattern. What is happening? Dot, dot, dot. Plus, and then finally the nth derivative. Good grief. Over n factorial times x to the n. All right. So that's the general solution. That's the general formula for a Taylor polynomial of degree n near 0. Okay, so only near 0. So now let's apply it. So example 4 is just using that formula to construct the Taylor polynomial of degree 7 for e to the x, again, near x equals 0. So let me scroll down here a bit. And so all we really need, I'll just keep that formula up there at the top. All you really need is the value of the function at 0, the value of the derivative at 0, the value of the second derivative at 0, and so on. And then you just plug those values in. So we can find easily that f of 0 is equal to 1, right? And so f prime of x, we already saw, is e to the x. The second derivative of e to the x is e to the x. And the third derivative of e to the x is e to the x. So, and that just keeps repeating. So we don't actually have to compute all 7 derivatives. We can just kind of see the pattern and go from there. So that means that f prime at 0 is equal to 1, f double prime at 0 is equal to 1, and so on, right? So that pattern is just going to continue. All these derivatives at 0 are equal to 1. So that makes our job pretty easy. And then it's just a matter of then plugging those values into the formula, right? So we have P7, so n is 7, of x is equal to 1 plus, all right, 1 times x is just x. All right, I'm just going in and putting the values into the formula. So the next term is, we have the second derivative at 0, so is 1 over 2 factorial, which is just 2 times x squared. And then the third derivative at 0, which is again 1 over 3 factorial, which is 3 times 2 times 1, which is 6, x cubed. And we got to keep going though, because we want the 7th degree polynomial. So we're going to get, you can kind of see the pattern. We have 1 over 4 factorial. And I think I'll just write these as factorials. X to the 4th plus 1 over 5 factorial, x to the 5th plus, let me go back. I'm going to write it, the rest has to go down here. So 1 over 6 factorial, x to the 6th plus 1 over 7 factorial, x to the 7th. All right. So that's our Taylor polynomial of degree 7. Now we could also look at, we could put in a value like we were doing before. We put in 0.1, 1/10, and looked at how good of an approximation that is. And this one is so good that if I put 0.1, if I can compute, let me back that up, P7 at 0.1, and I subtract the value of 0.1 e to the x at 0.1 on my calculator, using the value I get from my calculator, it's 0, given the precision of my calculator. All right, so that's just kind of a side note that that at least at that point, at 0.1, it's a pretty darn good approximation. Even better. All right. Well, the next thing we're going to look at is, what if we want to model a function not near x equals 0? What if we want to generalize and evaluate a function near some point other than 0? All right, so I'll meet you in the next video to talk about that.